Hello, this is Mrs. Jones and welcome to my lesson on energy efficiency. Hopefully you've watched the first lesson of the topic on energy stores and transfers, and this follows directly on. So we're going to have a look at Sankey diagrams again. We're going to have a look at useful and wasted energy transfers. We are going to look at calculating efficiency for energy transfers, and also if you are a higher tier pupil, we're going to look at how we can improve and increase efficiency of machines. So to start this lesson, we're just going to do a quick recap quiz, and all of these questions should be able to be answered if you've watched the first video on energy stores and transfers. So just pause the video, see if you can write down the answers to the questions here for this quick recap quiz. That's a bit of a mouthful, and then come back for the answers. Okay, so hopefully you've had time to go through and see what you can get for each of these. So for the first one, you should have got joules, or capital J, named after James Joule. For number 2, the answer is thermal. For number 3, the answer could be any of the following: heating, convection, conduction, radiation, or evaporation, but by heating really is what we're going for. Covers everything. For number 4, you should have got chemical and kinetic. For number 5, you should get 100 joules. For number 6, you should get by heating. Number 7 was gravitational potential energy, or GPE. Number 8 is kinetic, which is then transferred to elastic potential and then back to kinetic store again. Number 9, we're looking at kinetic store, and then that is converted to a thermal store in the brakes or in the surroundings. And number 10, you could have had anything from food, fuel, or batteries and cells. These questions did get a little bit harder as you went from 1 to 10, so hopefully you did well. So here I'm just recapping something that we did cover in the previous lesson, which is the law of conservation of energy, that energy can't be created or destroyed, so you can't make energy, and it doesn't just disappear, it just transfers from one store to another via energy transfers. But sometimes energy, or most of the time, energy gets converted to less useful forms and energy is wasted, so we say that this is dissipated into the surroundings by heating. The reason why we needed to recap this is because we need to remember this idea throughout today's lesson when we're looking at different energy transfers and how we can represent them when we come to calculate efficiency. This idea is important. Conservation of energy, and looking at this little animation of bouncing ball, I want you to have a quick think about why the ball loses height as it bounces. So if you drop a ball without putting any force behind it, it will bounce and it will never reach the previous height that it reached. So pause the video, have a think about how you would answer this question. Okay, so you might have come up with this idea that some of the energy is being wasted or transferred to the surroundings by heating and sound. And we talked about this last lesson, that sound is a mechanical wave, but it does end up, the energy does end up stored in the surroundings as thermal energy. So as the ball bounces, some of the gravitational potential energy that it stored at the beginning and the kinetic energy that it stores as it's moving through its bounce will be converted to energy that goes into the surroundings and stored as thermal, and this is the reason why it doesn't reach the same height. So the height that it reaches gets less and less each time until it eventually stops bouncing and stops moving. So we can represent this idea of some energy being useful and some energy being wasted using a thing called a Sankey diagram, which is a type of energy transfer diagram that you need to be able to interpret. So what I've done here is I've written some clues that I want you to have a look at, and then what I want you to do is I want you to use the clues, the information in the clues, to see if you can sketch a Sankey diagram for a light bulb. And it tells you here that energy is being transferred by electricity into 5 joules of energy transferred by light and 7 joules of energy transferred by heating. So thinking about what we've learnt so far and using these clues, I want you to draw a Sankey diagram, even though you've not seen one, and then what we'll do is on the next slide we can compare what you have got to what I've got and see how close you were. So have a look at this and have a look at what you've done and see how close it was. It might not be perfect, it might not be anything like what I've got here, but this is what we were aiming for. So the Sankey diagram here is showing us that 12 joules of energy was transferred to the light bulb by electricity or electrically. So this is the input energy. We've got 12 joules of input energy. And the width of the arrow, like it said in the clues, gives us the amount of energy. So it needs to be proportional. It needs to represent the amount of energy that's being transferred. So this width of this arrow represents 12 joules. Then we've got the useful energy, which is the 5 joules energy transferred by light, because it's a light bulb and that's what we want it to do, produce light. And the width of this arrow should represent the 5 joules and should be comparable to the width of the 12 joule arrow. Same with the 7 joules here. So 7 joules of energy wasted by heating. The width of this arrow for 7 joules should be slightly bigger than the width of the 5 joule arrow, and these two, 5 and 7, should add up to 12. So the width of the arrow is the important. It's not the length of the arrow, it's the width of the arrow that counts when you are drawing a Sankey diagram. So once you've had a look at this, what I would like you to then do is have a go at sketching a Sankey diagram. Now you know what it looks like, or draw something similar to this for a kettle. So like I said in the previous lesson, that kettle's a classic example that's used quite often, and it tells you here that 1000 joules of energy is transferred to the kettle and 850 joules ends up stored in the hot water. So what I want you to do is produce a diagram similar to this one for the kettle, and then we'll go through the answers on the next slide. There's a challenge here as well for you to draw a Sankey diagram for a television, and for this one you can make up your own numbers for energy values. So first of all, there's a couple of things that we need to work out from the information. The first thing is what's the kind of input energy that we're dealing with. So we've got 1000 joules of energy transferred to the kettle and it's plugged in, so the energy is being transferred to the kettle electrically, and that's the input energy. It tells them the information that 850 joules ends up stored in the hot water, and that's useful because the kettle's job is to heat up water, so that's a useful output. And that leaves us with 150 joules transferred by heating, and that is wasted because it's transferred by heating to the surroundings, because only 850 joules of the 1000 end up going into the hot water and to heat it up for our useful energy output. And it's just important to note really that we've got the two output energies will add together to equal the input energy. Once you've done that, you can draw your Sankey diagram. So I've got the width of the arrow here that represents the 1000 joules of energy that is being inputted electrically, and then our arrow that points forward is our useful output. So I've labelled that energy stored in the hot water and said that it's 850 joules, and then what we have left over is our 150 joules, and the width of the arrow should represent proportionally the amount of energy, so 850 and 150 here, and that's energy that's transferred to the surroundings, which is wasted. So now I'd like you to just have a look at these two Sankey diagrams. One's for an old style light bulb and one is for a low energy light bulb, and what you can do is just pause the video and compare the two and see what you can say about them, what's the same about them and what is obviously different about them. Okay, so hopefully you've had a little bit of time to have a look and compare these two. So the first thing to notice is that the amount of input energy is actually the same. So both of them have 100 joules of energy being transferred to them electrically. So the input energy is the same. But if we look at the low energy light bulb, it transfers much more of that energy usefully. So 45 joules out of the 100 are transferred by light. So that's useful because it's a light bulb, and also less energy is wasted. So when we compare two devices like this, the one that wastes less amount of energy proportionally to what goes into it, we say is more efficient. So on the next slide we're going to have a look at efficiency and how we might calculate it. So at the top of this slide we've got a definition for efficiency, and it's a way of measuring how much of the input energy is transferred to the useful output energy, but we can actually calculate it as well and give efficiency a number. The efficiency always has a number between 0 and 1 because you can't get anything that's either 100% or more than 100% efficient. So it's always going to be a decimal, it's always going to be between 0 and 1. So to calculate it, we take the useful amount of energy transferred in joules by the device and we divide it by the total energy that's actually supplied to the device. You can write it in a shorter way and just say that efficiency is useful energy output divided by total energy input, and these are both joules values. This is one of the equations that you need to remember for the exam. So you might be asked to calculate efficiency and they won't tell you what the equation is. So it's something that you need to go into the exam remembering. You could do that by memorising the triangle instead, which is the one in the bottom right hand corner. So here's the Sankey diagram for the kettle that we looked at a little bit earlier. And what I want you to do now is use the equation from the previous slide to see if you can calculate the value for efficiency for this kettle. Okay, so hopefully you've paused the video and you've had a go at calculating the efficiency. So the first thing to do is look for the amount of energy that's been transferred usefully. So we've got the 850 joules of energy is stored in the hot water, which is the useful, and then we need to divide that by the energy that has been supplied to the device, which is 1000 joules. So to calculate the efficiency, we do useful divided by total, that's 850 divided by 1000, which gives us 0.85 for our efficiency. Best thing to do now is to check that you've got a number between 0 and 1 and you've not got a number that's more than 1, because the temptation is, as ever, to divide the bigger number by the smaller number, and that's a common mistake that people make on these questions. This is the same as 85%, so it's either 0.85 or 85% efficient. Okay, so what you can do now is have a little bit of a practice. Have a look at the information in this table, pause the video and see if you can calculate the efficiency for these 4 examples. Okay, so hopefully you've had a chance to have a go at these 4 examples, and for each one of these to calculate the efficiency, you're looking at getting the useful value and dividing it by the total energy that's supplied, or the total input energy. So if you do that for each of these, you get 0.8, 0.25, 0.4 and 0.85. So have a look at your answers and check you got the same. If you didn't, have a look back and see where you might have gone wrong. Okay, so there's a couple more questions here using the same equation, but for these 2 questions you have to rearrange the equation, or you can use the triangle. So pause the video, have a look at these 2 questions and see if you can work out the answers. So for the first one, it's asking how much energy is transferred to the device, so what's the input energy, and for the second one it's asking how much energy is useful, so how much energy is transferred by light. So pause the video and have a go and then come back for the answers. Okay, so hopefully you've had time to have a go at these. I've got the triangle down here just to refer to if you're not sure how we came to the answers. So for the first one, it's telling you that a device transfers 20 joules of useful energy. So the useful energy is the 20, which is going to be on the top of the equation. And then we're going to divide that by the efficiency of 0.8. So the efficiency is here on the bottom. So if you cover up what you're trying to work out, which is the total energy, it tells you to do useful energy divided by efficiency. So if you do that for the first one, it gives you an answer of 25 joules. Best thing to do then is to sense check your answer. 25 joules is greater than 20, and we're trying to work out the input energy, so that makes sense that more energy is supplied to the device than is transferred usefully, so that answer makes sense. For the second answer, we are trying to find out the useful energy, so if you cover that up, it tells you to do the efficiency times by the total energy. So we've got 20 joules of total energy and 0.45 or 45% efficiency. If you times those 2 together, you get an answer of 9 joules. Sense check your answer. 9 joules is less than 20 joules, which was the input energy, so your answer makes sense. It's 45% efficient, so it should be just less than half. 9 is just less than half of 20, so it makes sense. So hopefully you can remember at this stage what the word dissipated means, because we talked about it last lesson and towards the beginning of this lesson. But no energy transfer is 100% efficient. Some energy is always wasted. What happens to it? It's dissipated. So that means that it's spread out to the surroundings and it's not useful anymore. We're not able to use it, and it's usually transferred by heat in some form. So I want you to pause the video and have a think about this question. What could we do to reduce the amount of wasted energy in machines? So pause the video, have a think, and then come back for the information. Okay, so the answer to that question is lubrication. We can use oil or some oily type substance to lubricate the parts of machines and help them to move past each other more smoothly. And that means that there is not as much friction between the moving parts. They slide past each other more easily, and if we can reduce the friction, we can reduce the energy that is transferred by heating. So if you get asked about lubrication, usually worth 2 marks, so you've got to say that it reduces friction and then less energy transferred by heating, and you can say sound as well, because that's also true. And sound ends up as heat or thermal in the surroundings anyway. What effect does this have on efficiency? Well, if you're going to reduce the amount of wasted energy, you're going to be increasing the amount of useful energy transferred compared to the input energy. So what that ends up doing is improving or increasing the number for efficiency for the machine. Now we can go back to this table. You've already done the first 4 questions earlier in the lesson. So what I want you to try and do now is work out what the missing values are here for useful energy and total energy. So use the information on efficiency and the other bits of information that you've got here to work out the missing values. So pause the video, work them out, and then come back for the answers. Okay, so hopefully you've had time to have a think about these. So for the first one here, we've got 1,200 joules is supplied and it's 0.9 or 90% efficient. So if you times those two together, 90% of 1,200 is 1,080. So we do the same with these. We've got 5,000 supplied and 95% efficient. So if you times those together, you've got 4,750. And the same with G, 750 times a 0.3, so that's 30% efficiency, is 225 joules of useful energy. For the total energy supplied, we are trying to work out the total energy supplied, which is on the bottom of the equation. So what we do here is we divide the useful energy by the efficiency. So for H, you end up with 500, for I, you end up with 400, and for J you end up with 50. So that makes sense because the total energy supplied is always going to be greater than the useful energy that is transferred. So here's an optional activity just to finish off. What I want you to try and do is use only shapes and symbols to answer the following, or to show what efficiency means and how do we calculate energy efficiency of any energy transfer, and you can only use shapes or symbols, you can't use words or numbers. Good luck! And that brings me to the end of my lesson on energy efficiency. Thanks for watching. Bye!